So let's stick to a practical example. We've got a 12-volt battery, so that's all. The 12 volt describes completely the battery. Yeah? And the other thing is the battery here is an ideal battery. Because normally, if you draw more current from a battery, then the voltage will drop. But with this battery, it gives you all the time 12 volts, no matter how much current you draw from the battery. Yeah? That's an electronic battery, that's a power supply. And here, so in circuit theory, we cannot calculate this circuit if we have physical wires in there. Yeah? Because a physical wire has a resistance. To calculate the circuit, you always have to do some abstractions. Now, the physical wire is abstracted by an ideal wire that has no resistance and a lumped element. This is called a lumped element. And this summarizes all the properties of the physical wire. And what's the properties of the physical wire? It's just a resistance, R1. Since we have more than one resistance in our wire. So that's one very important step. You've got a physical circuit that's out there somewhere, and you have to do some abstraction. So we abstract the real battery with an ideal battery. The ideal battery is characterized that it will give you all the time 12 volt, no matter how much current you draw. If this doesn't hold true, then it's impossible to calculate this circuit with simple calculus. Then you have to do a computer simulation on that. And also the wires. With a real wire, you cannot do a calculation. Because a real wire has resistance and all these things.
Every single point has a resistance.
Every single point, yeah. And all these single points are lumped together to one single element. To the resistance.
Well,
and this resistance we put in our circuit diagram. So you can have as many resistance as you would like. So that's why we sometimes call this an equivalent circuit diagram. So it's an abstraction of the real circuit to some degree. It might be enough, it might fail, the real circuit. That depends on your knowledge of the real circuit. So that's our lamp element, and that's why this kind of calculation is called lumped circuit element theory. So all the properties of the practical circuit is combined to one single element. You cannot abstract the whole circuit, but you can abstract the resistance of the wires. You can calculate it, and then you put in this single resistor. The rest of your wire is lossless. So all the connections in our equivalent circuit diagram is lossless. That's very important. It eases your calculation. The next thing we got here is our bulb. The bulb is nothing different than just another resistance. It's R2. And then we have the upper line. It's also just a lamped element, R3. The properties might be the same as R1. R2, R1. So, what is the size of R2?
R1.
And these R's are just called resistances. That's an ohmic resistance. Yeah. You can buy resistances, or you just get them in your circuit by nature. So every practical circuit has practical wires, and every practical wire has a resistance.
So in the electrical poles we add resistance if we want to drop the voltage, right?
Yeah, that's one main purpose of a resistance in an electronic circuit. You can drop voltage.
ECD stand for what? ECD.
Equivalent circuit diagram.
So, in this circuit, the second cycle there is the bulb.
R2
Yeah,
is
yeah.
the bulb.
Yeah, and the first cycle is what? No?
This?
This cycle here.
This is the upper wire.
Okay.
So here we also have
And the other one?
and the rest,
Yeah.
this is lossless.
Okay.
So all the resistance of these wires is lumped together to this element. And with this element we can do our calculation.
Okay.
Because for this we got some equations, we got Ohm's law. It's not much, but at least the starting point. And all the remaining connections, and that's also an important point, all the remaining connections are lossless. Because if the remaining connections is still a physical connection, then you cannot do a calculation. Yeah? So that's one important point. All remaining connections are lossless, so that the resistance is zero. All the resistances are lumped together to these elements here. So that's the abstraction we have to do. And it depends how complicated your circuit gets, to which degree you have to do your abstraction. And now we can do our calculation. What we have to know is the value of our resistances here. Right?
We can add it together, I think.
Yeah. So this depends on a physical circuit. If we got 10 meters, and I don't know, we got a small wire, maybe the cross section is 1 square millimeter. Right? That's a feasible size. That's the normal wire we use for house installations or whatever. Huh? So it's for power transmission. In electronic circuits, the wires sometimes get much more smaller than that.
Millimeters.
Huh?
Oh.
It's
What?
1/100th or 1,000th of a millimeter. If you've got a really small wire. So if we do the calculations, we have 10 meters, we have 1 square millimeter, and what we are missing here is this rho. This is the specific resistance related to the material. This only depends on copper. And for copper it's 1/75 or
57.
You can look up these numbers at
The difference from-
Wikipedia or physics book, whatever. But that's copper. Copper at,
That is constant.
there's a constant, yeah? It's copper for 0 degrees Celsius or 25 degrees Celsius. Let's say 25 degrees Celsius.
Do we have to learn them by heart?
No, this is not that important. I'll give you the number just now so that we can do the example. Huh? I don't expect you to know what all these numbers. Huh?
The complete version of this equation include temperature too, yes?
That's a basic thing. every material, every conducting material exhibits a temperature response.
And one extra factor for this equation.
Yeah.
Rho multiplied by factor for
Now,
temperature.
if you are also including the temperature response, then you have to calculate the resistance is equal to R0 times 1 plus, let's say, alpha times theta, and theta is the temperature in degrees Celsius. So if you stick with 25 degrees Celsius, then since theta is in degrees Celsius, this cancels out. It means at 0 degree, theta is 0, and alpha is the temperature coefficient. That depends on the material. But since this value is normally given for 25 degrees Celsius, and we normally have 25 degrees Celsius around us, it's fine to stick with that number. But if you operate your circuit at 120 degrees Celsius,
We'll have to change
then
that.
you have to change that. But if you operate it with 10 degrees or 40 degrees, then you don't have to care about that. Because the number is that small. For practical electronics, you normally do not account for the resistance of the wires. Yeah? This is only for this special example. But if you're building a circuit on a circuit board, you don't care about the
resistance of
resistance
the wire,
wires. Yeah?
because it's so small.
It's so small compared to the other resistances in your circuit that you don't have to care about.
Excuse me. So if you want to calculate the resistance of the wire, when we don't have the information of the voltage and the current, we use that formula.
We don't have, so you don't need the information about voltage and current. That's the fine thing with Ohm's law. The resistance is not depending on current or voltage. If it will be, or if it would be depending on that, then the calculations are possible. If that's the point with semiconductors. Yeah? Then the internal resistance of the semiconductor is dependent on the voltage or current that is flowing to the element. And then you cannot calculate this with that simple calculus. It's not possible. No? Yeah.
And then if the wire in
So if you change the material, then the resistance will change.
And then if the wire in consideration is not copper, we'll just use L over A and forget about the
No, if it's not a copper wire, then you have to change this 1 over 57. Because this is the material specific constant. Yeah? So the resistance of the wire is only depending on the material and on the geometry. The geometry is given by L over A, that's length over cross section, and the material is this row here. Yeah? So that's the equation for calculating the resistance of a wire. No? It's not depending on voltage or current. Yeah? It's depending on the material, this row here, the length, and the cross section, yeah? And nothing else. No current, no voltage. Yeah? The alpha is the temperature coefficient. That is if you want to include the temperature level into your calculation. But don't do that. It's getting only more complicated. So we don't, for now, we don't use it. And normally with copper conductors you don't have to use it. Except you are designing maybe for a spaceship or something like this. Yeah? But then you have to get a little more knowledge than
Okay.
You gain the required elective module. For now, we don't care about the temperature coefficient. Huh? So if we fill in the numbers, we finally get 10/75, and the unit of resistance is the ohm. So you can do the calculation. Do you have a pocket calculator? So we only need a rough number.
Excuse me, the surface, I mean the cross section is in millimeter too?
The cross section is in square millimeter, and the lengths always have to be fitting in meters.
Meters, so the answer will be 0.175.
1.5.
No. 0.175.
Okay, ohms. So our wire has a resistance of 175 milliohms, or 0.175 ohms. So that's what we can put in here. Huh?
Mm-hmm.
So R1, it's 157 ohms. R3, since it is the same wire, it's 0.175 ohms. You see the ohm character, it's pretty complicated. That's why you will never see an ohm character in a circuit diagram. Normally you are writing 0R157. You also omit the decimal point, because in English it's just a point. Huh?
Yes.
And you can remember, if you copy the circuit diagram maybe 100 times, then you will not see this decimal point in the diagram. Therefore, for the decimal points we use R.
Okay. So it was
It's 0.157 ohms. 0R157.
175.
It's 0.175 ohms.
You're right, 157.
0R1. Okay, yeah. Huh? Also, if your resistance is 1075 ohms, then you write 1K75. Yeah? K. K is 1000.
Okay, yes.
Or if it's 1,750,000, you
1
write
M.
1M75.
Okay.
Yeah? So if you look into a circuit diagram, you will never see a decimal point because it will get lost. At least in the old times where you had the circuit diagram on paper. Okay, so we knew our resistance here. We knew our resistance here. What we're missing is our resistance R2. Do we have any information about R2? We have to look at the bulb. Huh? Maybe at the bulb it says P, it's 50 watt, and a 9 volt bulb. Because
So
in a 9 volt circuit we have to use, it's a 12 volt circuit, so we use a 12 volt bulb. So how can we get the resistance of this bulb?
We get the current and then
equation of P
yeah,
equal to VI,
and then we
get
calculate.
R equal to V divided by R.
Exactly. P, Joule's law, it's V times I, and there is the the V is R times R is 3 over R. And if, and what we would like to see is R. So R, we can put this here, it's mu squared R. Let's do it that way. P is u squared over R. So R is u squared over P.
What's U?
U is V, actually. Because in German it's always written U for voltage, so for me it's pretty hard to switch from U to V. It's V squared over P. So V squared is 144 over 50 watts. So it's roughly 3. Or you can do the calculation,
2.88.
2.88 R. So it's 2R88. And now we knew every resistance in our circuit.
Now we can calculate.
Now we can, what can we calculate now?
We have everything. We have the
We
voltage.
have everything, so we can calculate the
current,
current that is
yeah.
flowing. Huh?
I equals V over R.
So, how can we calculate the current?
I equals voltage divided by resistance. So we have the voltage 12 and the resistance.
And what do we use for the resistance?
The summation, sum of the.
Since the current is flowing through all resistances, we have to sum up all the resistances.
Yeah.
There is also another possibility to calculate this. What's the time now?
It's 3:27.
3:27. So the lecture is actually until 4 o'clock, but you got 10 minutes break in between. But since we
can continue.
it's not useful to take the break now, so maybe we continue to the end and 10 minutes early, 4 o'clock. Yeah?
Because if we win, I will forget everything.
So you have to sum up all the resistances in your circuit. So this is R1 plus R2
Plus R3.
plus R3,
Well, we have R1 as
and that, you see,
that's it.
the resistance of the wires still changes the current. That's what it's changing in our circuit. It changes the current, because it's down here. This is just a serial combination. We will go through that the next time, because there is also another model of calculation with Helmholtz equations, but that's not worth with this simple circuit. The current is flowing through all resistances, so you have to sum up all resistances. So it's 12 divided by
R1, that's for
So we can do the calculation.
So, I don't understand. How one is not 0.175.
Yeah.
Yes.
So how do you get it to
So because you
Two
have two
is since we
resistors.
got two of them,
Yes.
R1 and R3.
okay.
So
Two
it's-
times.
both of them are 0.175. So we got it 2 times in our circuit.
Multiplied.
Okay, one more.
Yeah.
3.70.
Seven, one, five.
3.715 amps. So you see, we got more than 1 amp, but 1 amp is at a special value. So and what is happening to our voltage? The question that still remains is, what's the voltage at the bulb? That we don't know.
What the voltage? Sorry again.
It's
What the voltage? Sorry.
That's the bulb
Uh-huh.
at the lamp there.
But
So what
we can
actually
know. We can know.
happens here is, at every resistance we have a voltage drop.
But we can know that's
The
not.
voltage drop, let's say delta V, not U, it's V, is R times I.
Yeah.
Yeah?
We
So
have.
we have 1 voltage drop here, we have 1 voltage drop here.
Uh-huh.
This we can calculate. This is 0.175 times our current,
3.715.
3.715.
715. Yeah. And also, we can
And the
calculate.
same we get on the bottom side here. Delta U1, delta U3, delta V3.
0.65.
0.65. Here also 0.65. So that means the voltage at the bulb U R2 is equal to, let's say this is U0,
Uh-huh.
minus delta V1 minus delta V3.
Uh-huh. Yeah.
0.65 is 1.3, so we get 10.7 volts.
But we can calculate it immediately without that.
Yeah, we can use Ohm's law for that at the bulb.
Yeah.
The resistance times the current.
Yeah.
Should give you the same number. Let's try. It's R2 times I is equal to 2.8 times 3.
3 point,
175.
no, 715.
715. Okay.
9.14.
This is
9
10, no, 10,
10?
10,
Yeah,
10,
10.
69.
Why it's not the same?
Then we have to do the calculation
Ah,
with
yeah, yeah,
more
it's,
number with a higher precision.
But it's almost the
But
same.
it should be the same, huh? But it's actually the surrounding error. Huh? You see, it's the same.
Uh-huh, yeah.
And what will happen if we lengthen the line?
If we,
What will,
sorry.
if we maybe we step from 10 meters to 20 meters?
It will, the resistance will
The
increase.
resistance will
Increase.
get twice as high, huh?
Yeah.
Since the length is double. So with this equivalent circuit diagram, you also easily can guess what will happen if you change some parameters of your circuit. Huh?
Yeah.
Okay, so we have 20 minutes left.
Yeah, 35.
50?
15.
15.
Excuse me, I have a question about things in atoms. We have another thing called positron in the atom.
Positron.
Not proton. Positrons.
Positron we have.
Nowadays we are talking about it. Would you mind?
But the positron is the antibody of the electron. So the positron normally will find any positron in a normal circuit.
Yes, we can't find it in the circuit, but we can find it in atoms.
Yeah. But you will have an annihilation, or what's called in English. So if you combine an electron and a positron, you will have only energy. So you can have electrons or you can have positrons, but you never can mix them. Because this will give you a big explosion.
So we don't have any separate things in the atom?
No.
Called
In electronics, you forget about positrons. They are not available in our universe. There might be a universe that's the same. You have positrons, but no electrons. Because this is the antibody. So if you combine them, they will give you a big explosion. It's antimatter. If you notice?
Yeah.
And your electron and the positron is the antimatter of the electron. But we have protons. This we have. But there is nothing to tell about protons in electronics. They are fixed in the core of the atom and this won't move. Yeah. Any other question? Because if we have only 15 minutes left, then it's better we do some questions related to this example than to start a new one.
No, you
So
won't.
practically, we have lost our 0.6 volts on R3, 0.6 volts on R1, and exactly we have utilized 10.69 volts to analyze both.
In practice, the voltage loss we have in this circuit across the resistance. But in practice, at the real circuit, the voltage loss will sum up along the line. Yeah? If you measure from here to here, you might have only 0.1 volt voltage drop. From here to here, 0.2, and if you come to the end, then you will see this 0.65. Yeah? We can do a measurement on this in the lab. Yeah?
So,
But that's the goal of the equivalent circuit diagram, because you cannot do a calculation with this growing voltage drop along the line. Yeah, that's not possible. Yeah.
so if we are going to put the current 3.715 in the diagram, where are we to put it?
The current,
Yeah.
that's the easy point.
Yeah.
The current is everywhere the same.
Okay.
If you measure here,
Yeah.
or here, or here, or here, or here, or here, or here,
Yeah, it's the same thing everywhere.
you always will measure 3.715.
Okay, good.
This we can also do in the lab. And the important thing on measuring current is you have to cut the wire. There are normally some connections, so you don't have to cut the wire all the time in the lab. And then you put in your ammeter. Yeah? You put in your ammeter and the readings will be 3.715, no matter where you put it in the circuit. Yeah? So also here in the line, you can make your cut everywhere. It gives you all the time the same reading.
The things which we calculated before, it shows that we don't have any losses of voltage when it passes after R2.
Yes, there is loss.
No.
There is loss. So if you take a voltage instrument and do your measurement from here to here, yeah, That's the basic difference of the two measurements. For current measurements, you have to cut the line, put your instrument in, and the current can again flow.
But I'm talking about this example because the answer will show that both are the same.
This 10.69, we have to use a voltage instrument.
Yeah.
And the voltage instrument you've got with one pin to the lower line, with one pin to the higher line. And if you do your measurement next to your battery, it will give you 9 volts. And the more you move to the other side, the closer you will get to 10.69, yeah?
So, and the answer on the bottom is the same, 10.7.
7, yeah. That's the same. But this was only a different kind of calculation. If you're doing the calculation with more precision, then it will give you 10.69, yeah? That's rounding errors, because we didn't use
69,
enough
9 to
decimal places, yeah?
Yeah.
But no matter which way you do it, it
So what
gives you the same number.
what's the consequence after these comparing these two amounts?
There's the consequence is that you have to do your precision with your calculation with more precision. So there is no 10.7. It was only a guess. Because I doubled the voltage drop here, it's 1.3. Yeah? But actually we will not see 0.65, it might be 0.58 something. Yeah? So that's a calculation error. That's not an error in our circuit or in our thoughts, it's a calculation error.
Can we make in the lab an example like take a bulb, take a small battery and mix
We
them
can do this, yeah?
to
And
see?
then you can measure along the line, and you will see that the voltage will drop.
Because I think it would be better for our...
Yeah, yeah. So then we can do this as our first lab experiment. It's a simple circuit, but it gives you all the things you have to.
Should we bring bulb and
Yeah.
batteries or we have everything here?
Now we will take a power supply.
Okay.
Because if you take a battery, then it will get complicated.
Why? Because we need just the wires. I did it once.
Yeah.
at home.
But if you, so it's part 3.
Part 3, okay.
Part 3. So if you take a practical battery, yeah, then you will have to observe the load line, and that's our load current, and that's the output voltage of our battery.
Well, we need to take a small battery because otherwise the bulb will just break down. Or...
No, if we take a 12-volt bulb,
Yeah,
it
but
will be okay with our
if we
12-volt
take a
battery.
small bulb
If
like
we take a
this,
small bulb, then we don't have enough current to measure the voltage drop along the line. Or we have to use a very thin wire. But we take a 12-volt bulb, and normally the battery voltage will drop the more you load the battery. So that means that if you load the battery with the bulb, you will not see 12 volt here. You will see maybe 11.8.
okay.
So that's zero current. That's 3 and 175. So
And
we will see
if we
smaller numbers. And the more tricky thing is, the longer you load the battery, the lower the voltage will get.
And if we make the additional power source, we will easily observe the loss in voltage more easily than with the normal battery, right?
Yeah. Because here we got stable conditions. no matter how long you do your experiment, you will have 12 volts.
Okay.
Huh? So that's why we normally use power supplies. And the other fine thing with power supplies is maybe it can happen you do a short circuit here, you make a miswiring, it happens sometimes.
And the current stops there, and you don't.
Then there is no limiting factor for our current, because here the bulb is limiting the current. But if we do a short circuit here, our limiting factors are only the resistances of the line.
Yeah, and there is no
This is
resistance. on the bulb.
1.3 ohms. So we got 12 over 1.3, it's roughly 10 amps. Then you got a real big current, and it might destroy something. In this case, it's not dangerous.
But in this one, it's dangerous.
It's not, yeah, with the battery. But with the battery, we see it here, 12 volts and a resistance of 1.3 ohms. Due to the wires, we end up with a current of 10 amps. But for the power supply, we can set the power supply for a maximum current of 4 amps. And if we got 4 amps, the power supply shuts off.
Okay.
So they are on the safer side. So, that's all the problems with the battery. What happens if you short circuit the battery? Then you go along this load line until the voltage is 0. And if you do this with your car battery, that gives you a spark. It might be 600 to 800 amps.
Well,
So if you use a normal wire, then the wire will explode.
no, the battery from.
The
Remote
battery from the
control.
remote control, it's
Okay.
no problem. Except
simple
that the
battery.
battery is gone. Yeah?
Yeah.
If you short it one time, then it's gone. But therefore, in the lab, we all the time use power supplies, because we can set the power supply for a maximum current. And if this maximum current is exceeded,
It's just that.
the power supply will shut down, so we are all the time on the safer side.
Okay.
If we try this short circuit with, for example, 12 volts battery, it just get heated after